Mathematical models are essential tools for understanding patterns and changes in real-world situations. In both natural and human-made environments, processes such as population growth and temperature change can be described and predicted using mathematical equations. These models allow researchers, scientists, and decision-makers to analyze trends, make informed predictions, and support effective planning or action based on observed behaviors. One common application is the study of living organisms and how they grow or decline under various ecological conditions. Another is the analysis of physical processes such as how heat is transferred between substances, whether predicting how a species thrives in a suitable habitat or estimating how fast an object cools down in a controlled environment. Mathematics provide a reliable framework to simulate these events. By translating these real-world situations into mathematical terms, we gain deeper insight into how systems behave over time and how they respond to surrounding influences. Thank you. Okay, now I'll be presenting about Villa table, part A. Okay, first of all, facts. The first fact, the fish population in 2015 was 2,000. The population increased to 3,500 by 2020. Growth is due to favorable conditions and exponential growth is mentioned. Okay, ideas. First, exponential growth follows the model. Second, let t equals to 0 in 2015, so t equals to 5 in 2020. 3. Calculate using the known population values. 4. Use the equation to calculate future growth. Learning issues. First one, how do we derive an exponential model using two data points? How do we estimate future population using the exponential model? What are these implications of continued exponential growth? How accurate is exponential growth over a long time? Action plan resources need. Use the formula and known values to find the constant into the model to find the population. Discuss population sustainability and potential need for a logistic model later. Interrupt the result and suggest ecological monitoring for long-term balance. Thank you. Okay, and now I'll be presenting about problem. In a protected freshwater lake, environmental researchers are monitoring the population of a specific fish species. This species is thriving due to favorable ecological conditions such as an abundant food supply, clean water, and reduced predation. The fish population was recorded at 2,000 in the year 2015. After 5 years, in 2020, the population increased to 3,500 following an exponential growth pattern.
This is our solution for part A. First question is, we need to derive the representing equation of the fish population at time t. So we need to create the general formula for exponential growth, which is pt equals to to the power k times t, where pt is population at time t years, p is initial population, k is growth rate, t is time in years. For the first step, we substitute 5 into t, so we can get 2000 e to the power 5k equals to 3,500. Then we bring 2000 to the other side, we get e to the power 5k equals to 3,500 over 2000, and we get 1.75. Then we multiply both sides by ln, so we can cancel out e. Then we get 5k equals to ln times 1.75. So we bring 5 to the other side, we get k is equals to ln times 1.75 over 5. Then we get k equals to 0.112. So the final general equation for our solution is pt equals to 2000 e to the power 0.112 times t. For the next question, we need to estimate the fish population in 2025. So for the solution is, we know that 2015 to 2025 is 10 years apart. So our t is equals to 10 years. So next step is we substitute 10 into to T, we get T10 equals to 2000 e to the power 0.112 times 10. Then we get T10 equals to 6129. So the fish estimation in 2025 is 6129 fish. For the next question, we need to predict when the fish population will reach 10,000 fish. So for the solution is, we take our general equation from we derived earlier. So we get 2000 e to the power 0.112 times t equals to 10,000. We bring 2000 to other side, so we get 10,000 over 5. Then we simplify it, we get e to the power 0.112t equals to 5. Then we multiply both sides by ln, so we get ln times e to the power 0.112t equals to ln5. Then we can cancel out ln and e, and we get 0.112t equals to ln5. Then we bring 0.112 to other side, so we can get t equals to ln5 over 0.112. We can solve it out, so we can get t equals to...
Here, let's talk about the discussion for part A. The exponential growth model reflects how populations grow when environmental conditions are ideal. In this case, clean water, plentiful food, minimal predation are the main factors of growth. The solution shows constant percentage growth and it fits well with the observed data between 2015 and 2020. From the model, the population increased from 2,000 to 3,500 over 5 years. If these ideal conditions continue, the population is projected to more than triple in 10 years, reaching over 6,100 by 2025. However, we can't really depend on the equation above because the exponential growth may change because of other factors such as lack of food, resources, and environmental changes.
In conclusion, the exponential model was successfully derived to represent fish growth population over time. The equation Pt equal to 2000 e to the power of 0.112t is used to calculate fish population growth. This growth reflects a thriving aquatic ecosystem, but future management should consider transitioning to logistic growth models as the population approaches environmental carrying capacity to avoid overpopulation and ecological imbalance.
So this is the FILA table for part B. FILA means facts, ideas, learning issues, and action plan or resources needed. Let's dive into the facts. Number 1. The initial soup temperature is 180 degrees Celsius. Number 2 is room temperature of 20 degrees Celsius. Number 3 is the temperature after 20 minutes, which is 100 degrees Celsius. And number 4 is target temperature of 80 degrees Celsius. Next up is ideas. Number 1 is to use two known temperatures from 180 degrees Celsius to 100 degrees Celsius in 20 minutes to calculate the cooling constant. Number 2 is to apply Newton's law of cooling formula using that K. Number 3 is to treat 100 degrees Celsius as the new starting temperature. And finally, number 4 is to solve the exponential equation to find the time taken to reach 80 degrees Celsius. Now let's move on to the learning issue. How to use Newton's law of cooling in real life problems. How to solve exponential equations using logarithms. And number 3 is understanding the role of the cooling constant. And number 4 is interpreting and applying temperature time data accurately. And finally, we move on to the action plan or resources needed. Number 1 is to identify known data, initial temp, final temp, room temp, and time. Number 2 is to substitute values into Newton's law to find K. Number 3 is to formulate the second equation to calculate time to 80 degrees Celsius. And finally, solve using natural logarithms.
Okay, problem. You place a pot of hot soup on the counter in a room where the temperature remains constant at 20 degrees Celsius, allowing it to cool naturally. Right after removing it from the stove, you measure its initial temperature and find that it is 180 degrees Celsius. As time passes, the soup gradually loses heat to the surrounding air. After 20 minutes, you check the temperature again and observe that it has dropped to 100 degrees Celsius. Knowing that the soup will be cool enough to eat once it reaches 80 degrees Celsius, determine how much time it will take for the soup to cool down from 100 degrees to 80 degrees.
Next is the solution for part B. First of all, we need to state the Newton's law of cooling formula, which is T equals to T room plus in bracket T0 minus T room times e to the power negative t times t, where T is equals to temperature at time t, T room is room temperature, T0 is initial temperature of the soup, K is cooling constant, T is time in minutes. So next step is, we given T20 equals to 100 degrees Celsius. The next step is we need to solve for K. So we substitute 20 into T. So we get T20 equals to 20 plus in bracket 180 minus 20 times e to the power negative 20k. So we get 20 plus 160 times e to the power negative 20k. We get 100. We bring 20 to other side, so we get 160 times e to the power negative 20k equals to 80. Then we bring the 160 to other side, so we get e to the power negative 20k equals to 0.5. Multiply by both sides, so we can cancel out e. So we can get negative 20k equals to ln times 0.5. So we can bring negative 20 to other side, so we get k equals to negative ln times 0.5 over 20. So final answer for K is 0.035. So the next step is we need to find T for 100 degrees Celsius to reach to 80 degrees Celsius. So we can write the equation as 20 plus 80 times E to the power negative 0.035 times T equals to 80. So we can bring 20 to other side, so we get 80 times e to the power negative 0.035 times t equals to 60. Then we bring 80 to other side, so we can divide. Then we can get e to the power negative 0.035 times t equal to 0.75. And then we multiply both sides by ln to cancel out e. So we can get negative 0.035 times t equals to ln times 0.75. Then we bring the negative 0.035 to other side. We can divide it by ln 0.75. We get t equals to negative ln times 0.75 over 0.035. Then we can get e equals to 8.22. So in conclusion, it will take 8.22 minutes to cool from 100 degrees Celsius to 80 degrees Celsius.
This is the discussion for part B. This problem is a classic application of Newton's law of cooling, showing how temperature decreases in a non-linear exponential fashion. The soup cools rapidly at first when the temperature difference is large, then more slowly as it approaches room temperature. We use the temperature readings at two known times, initial and after 20 minutes, to compute the rate of cooling, K, which characterizes how quickly heat is lost to the environment. Then, we model the second cooling interval from 100 degrees Celsius to 80 degrees Celsius using the same cooling rate.
In conclusion, Newton's law of cooling effectively models the rate at which hot objects like soup